Hi everyone, good morning. My name is Matt Singer. I am a staff hardware engineer at Twitter. This is Nick Johnson. He's a software engineer in our provisioning team. We're going to give this talk in two parts. I'm going to start out kind of going through our server infrastructure, give you some insights into that. Then later, Nick will talk about how we provision all those servers. The whole day's track is really going to talk, we're going to go all the way from the metal to the tweet. So I'm going to start out telling you what all the choices we've made to make our fleet inexpensive, reliable, and fit our application really well. We've approached designing servers in a certain way to help us scale, and scale really easily. So today we're going to talk about really four things. We're going to talk about how we think about the fleet, how we kind of model the types of servers we want to buy, and we're going to talk about the characteristics that we want to get out of those servers. Then I'm actually going to show teardowns of some of the legacy systems we had before we started designing our own servers, and then I'll show you teardowns of the first generation servers that we designed to replace those. I want you to look at how some of those simple changes in those servers really make a pretty big difference in the reliability, the costs of doing this yourself. You get a great payback by doing it. And then when I get to the end, I'm going to be able to show you a little bit of reliability data to show you that this really did improve our experience with servers at Twitter. So this section is about how we thought about our servers. So we have three major classes of things that we found that we were deploying. And this was even before we decided to design our own servers. We have these servers we call front ends. This is a server that is really dictated by the amount of memory in the server and the amount of compute power we need in the server. Storage is really about a boot disk, about booting the system. Persistence is done somewhere else in the application layer. We didn't need certain things in that server because of that. Then, the next major class of servers we had were storage servers. This was very much the opposite of what we had with the compute servers. This server was dominated by the storage capacity it needed. This was a large number of 3.5-inch disks, and really by and large, the compute power that this server needed was drastically different. Then the third kind of server that we found we were buying were these database servers. And this is kind of your no compromise server. You want hot plug, you want a RAID card, you want to make sure that it has plenty of memory, that it has plenty of compute power, so that no matter what you throw at it, when data consistency is your most important thing that you want out of it, you've got it. So we've taken on all three of these categories of Twitter. Today I'm only going to talk about the front end and the compute node, the front end node and the storage node, because that's where the big opportunities were, because those were deployed in much larger numbers than the database servers. So, like most companies that would be doing this, we started out purchasing servers from the big brands. When we looked at what these companies were trying to do, they were trying to design a server that had the widest appeal. No matter who came in looking for a product, they wanted something that would work for you. But that philosophy, when you're doing that, means that you're going to be selling a little too much to the customer rather than just what they want. So when you do that, those extra things in the server added complexity, they added cost, and believe it or not, they added failures. And I think we'll kind of see how that works out later in the presentation. So what did we want? It was more about what we didn't want in these servers. We really, in most of the fleet, didn't want hot swappable disks. We didn't want to buy SAS disks. We didn't want a lot of RAID controllers, because we knew operationally those were problems for us in the past, and we weren't really using them to our benefit. The other thing we didn't want on the server was we didn't want their logo on the server. Because you pay a lot for that logo, because that company is convincing you that their validation of these servers is superior, you're going to have less problems. In general, I don't think we found that to be the case. So we made a lot of trade-offs. We got rid of hot plug. That was one of our biggest design simplifications in a tremendous amount of our servers. When you look at how that worked out at scale, when you are racking servers by the truckload, you know that 99% of these servers you're not going to have to service. And the economics of that really changes at that scale, that you don't want to pay a certain dollar amount for a feature that you're not going to use every year or even maybe over the life of the server. So serviceability became less important, although our servers actually are surprisingly serviceable even though we don't have hot plug disks. And that's the one major thing that I want you to think about this talk, is we got our engineering gains from simplifying the hardware. So the first server I want to talk about is our storage server. So really it was about the opportunity we had. The server we were buying for what we were doing was too much server. We had hot plug support for 12 drives, and that ended up dictating the physical size of the machine to 2U. That hot plug support was in an active mid-plane that had a SAS expander. That thing was a problem for us in terms of reliability. There was a problem getting enough data off of the disks to feed the expensive CPUs that were in that system. So we needed to switch to a different CPU that was a better match for our ability to get data. We ended up with an E3 CPU that turned out to be a great match for data processing ability, for our ability to pull that data off of the disk. And then we wanted more control. When these servers failed, if you were buying this from a big company, it could take quarters for a fix to get identified, rolled into the main line with the code that's going to go out to every other customer. Then you got your fix and a bunch of other things that other people wanted that ended up not working well for you. So we were able to fix issues faster because of that. And then we obviously, what everybody wants, we want to pay less. When you do this and do your own server, you're going to be able to negotiate on every commodity in that server. You're not going to be pitting company 1 against company 2. You're going to be pitting 3 or 4 drive manufacturers against each other, 3 or 4 RAM manufacturers against each other. And you're going to get a much lower price on every piece of that server. So who wants to see some teardowns of these servers? This is one of our early storage servers. You can notice that the chassis is 2U high. That's because of the way the drives were inserted. And that's really because there's a mid-plane in there for that to support that hot plug. I have a couple comments about that. It fails. It needs firmware updates. Those firmware updates, most of the time, I won't say most of the time, that firmware update frequently kills it. It's also, you're trying to move air from the front of that case to the back of that case, and you've got a wall there because of that. So your thermal design gets a lot more complicated. So I want to get rid of it. Next thing we have in that case is this hot plug power supply. because it's a hot plug power supply, it needs to mate to a power distribution board, and there's this company integrated in a fan control board. Those were two things that ended up failing. The power supply never failed, but one of the little boards it was attached to would fail. So we really want to get rid of those two. Now we have dual CPUs. We couldn't get data off the disk fast enough to keep those CPUs busy. So we were buying a class of CPUs that was relatively expensive, and those CPUs were spending a lot of their time idle. So we're going to get rid of one of those from our new design. So let me show you a teardown of the server that I replaced it with. You can, I think if I go back and forth between the slides, you can see how much less stuff is in this box. It's the same number of hard drives, but the arrangement of the drives, we went from 1U in the rack, or 2U in the rack, to a 1U server. So we can get twice as many of these into our rack. There's no RAID controller, there's no SAS expander, there's no backplane, there's no PVD. There's one thumb screw to remove the top chassis. Then you can just pop a drive out by hitting a tab. So even though we can't hot plug these drives out the front, when this machine needs service, pull it out, pop the cover off, pop the drive out, replace it. You still only end up removing 4 screws like you would to get it in and out of the hot plug bracket that any other company would have given you. So it's just about as simple as we were able to make this server. So the way that this changed was that we got twice as many in the rack. That was a huge win for us, right? Because when you're in a data, you're paying for a square foot of floor space, however many that is, that cost drops in half. You get more things into the same switch, you get a return on everything just from some density. Then we got rid of these several things that were big operational pain points for us. SAS expander, RAID controller, mid-plane. And we got into a cheaper CPU that was a better balance of compute to the server. And really, the question was, how did that work out for us? This actually did better than we thought it was going to do. We were able to swap these 1-for-1 for the 2U server we were buying before with twice as many CPUs. It was the perfect match for compute to storage for us. Then, once we had that going, and that was a great success, the server that we actually ship in the greatest numbers are our front-end machine. Like I said, this is something that supports mostly compute and memory. This is what goes into our huge Mesos fleet. So we took a similar approach. We wanted to simplify it and get it down to only what it needed to be. So here's the teardown of the old front-end system. This is my favorite. There's a SATA mid-plane for hot plug. This was, I didn't even realize how much I hated these things until I wrote this presentation. This thing obstructs airflow. This one was passive, so we really didn't have a failure problem with it, but we're going to get rid of it. Then the next thing that happened, because that SATA mid-plane was in there, there are 16 fans to try to move air through this chassis. Each one of those fans can draw 10 watts of power. If you are spending 160 watts pulling air through that server, that's as much power as you probably were putting into the CPUs. That almost drops how many CPUs you can get into the rack by 30–40%. And it costs you money every year that server's running. So we're going to end up getting rid of those. Then, one thing we never had a problem with failing were power supplies. This server came with dual power supplies. We approached redundancy to like utility feeds. I don't know if any of you have your own data centers. You'd like to keep 2 feeds going to the rack in case power fails. We took care of that with the transfer switch in the rack. The only thing that 2 power supplies were doing for us was trying to mitigate power supply failures, which weren't a problem. So we'll get rid of one of those. And I don't know if you noticed in the other teardowns, we had some screwdrivers in the picture. We left these screwdrivers in the picture to show you that this vendor decided we needed 4 different types of screws in order to disassemble this. So we're going to simplify it, make it easier for us. This is what we replaced that server with. Same basic capabilities, 2 CPUs, very similar amount of memory could be installed. Everything else is gone. We don't have a hot plug power supply, but these cables really coming out of that power supply are only 12 inches long. There's no need to do anything fancy. And we went from 16 fans down to 5 fans. At max power, I can save 100 watts because of that was wasted. Because it's really easy to get air in the front and out the back of this chassis. So we had less stuff to pay for, less stuff to draw power for years, and then less stuff to fail. So all 4 of these things together cut not only cost but reliability. These servers generally have 1 single boot drive in them. Hot plug was really not important. Going down from 16 to 5 fans, great power savings, really important in a data center when you're going to run these for years. And 5 fans fail less than 16 fans. And we went to a single power supply. What we really got out of this, we got a server that consumed less power, cost us less to run, cost less to buy. Did exactly the same thing. So you're probably going to say, prove it. I can't go into financial details. I wish I could. So many people would be so mad at me if I told you how much less this costs than buying a server from a big company. But I want to share some relative information on reliability. So let's talk about that. I have 3 systems on this graph. Can't talk in absolute numbers. I've removed the scale, the Y scale from this. But you can look at those 2 yellow lines. These are systems we replaced. These were the incumbents before we designed our own server. That one, normally up and to the right is good. In this case, it's bad. This server, as it's getting older, even coming out of 12 months of age, we're seeing accelerating failures. It was a server that had a component in it that had an unexpectedly short life. It was a big operational problem for us. The other yellow line that goes kind of down to the right, was a typical case for something from one of our OEMs. But what's really dramatically different is the blue line. That's the server, that's that front end server I just showed you that we replaced the other servers with. Our need to swap parts in those servers, I'll just say that's roughly 40% lower rate of needing to swap servers, or needing to swap components out of it. And we got that simply by getting rid of a bunch of stuff from the server. So that's a win any way you look at it. Cheaper, more reliable, and you get to own your design and own how you repair things and when you fix things. So, quick recap. Things got cheaper, things got more reliable, they fit our needs exactly, they drew less power, and we were able to resolve problems faster. And there's really one reason we did that. We simplified everything. That's what I want you to walk away with today if you decide to buy servers. Now, I will take questions on my section at the end of Nick's talk. Nick is going to get up here and address a problem that is analogous to this. I am bringing servers in literally by the truckloads into the data center. You have to get those servers ready to use. In the time that we are going to spend in this talk today, we can deploy those truckloads of servers and have them up and running. Nick is going to tell you how we're going to do that.
Question.
I'd like to take those.
Yeah.
So
Who here has installed an operating system before? Then you know. I remember installing Windows XP back in the early 2000s. I had no idea what it was doing, and it took hours for Windows alone to install. Today, I can get Debian installed in about a half hour. But that's without installing your favorite internet browser, your favorite email client, configuring your calendars, or installing Skype if you use that. At Twitter, we can do the entire process, including installing all the applications, in a half hour. And we can do them a truckload at a time. The big question is this easy to achieve? Is it worth it? And the answer is yes. So I'm here to tell you that provisioning at scale can be fast and easy. I'm going to talk about the three main components that we use for provisioning. Collectively, we call this the Wilson stack. First, there's Wilson provisioning, which handles basic control and automation. There's Wilson API, which provides our automation for a sequential task we want to do on a server. And lifecycle, which provides an abstraction layer on top of that, which is what we primarily use to manage servers and install. Wilson provisioning. To control hardware, we need to be able to instruct it to run arbitrary code independent of whether or not an operating system is installed on it. These things don't come from the factory with an operating system pre-installed. The earliest point in the boot process that a server can talk across the network is during Pixie. These servers all come from the factory, configured to boot over the network card to a Pixie server. And so they are literally plug and play at our data center. For those who don't know, Pixie stands for Pre-Boot Executable Environment and allows the BIOS to boot over a network. By generating a dynamic Pixie menu from Wilson provisioning, we can instruct the server to either boot to the local disk or to download a custom RAM disk and kernel that we choose, that we call the Wilson image. When a server boots up and asks for a Pixie menu, Wilson generates a default entry for the action we want to take that we call a stage. If we don't provide one, then we boot to local disk. However, if a custom action is taken, it pulls down the local image, boots into it, examines the command line parameters that we passed on the Pixie menu, and says, okay, I need to boot into, say, the BIOS update stage. It will then talk to Wilson provisioning again and say, hey, I need everything I need to run the Wilson or the BIOS update stage. And it will download, it's basically just a list of bash scripts or Python scripts depending on the application. And it downloads them and runs them. At the end of that, it will talk back to Wilson and say, okay, I've completed that stage and I'm going to reboot now. It will reboot and the process will repeat until it is out of task to run and will boot into the local disk, which hopefully is an operating system. One note though before we continue, Pixie by default uses TFTP, which is the horrendously unreliable protocol. We found this through lots of testing that the best way to netboot a fleet of servers is to actually first download a program called gPXE, which is essentially a small executable environment that replaces Pixie itself. And this image actually has a full TCP and HTTP client built into it. So you can actually use HTTP to download all your necessary resources. This primarily comes into play when there's network congestion and packets are being dropped. gPXE is able to handle that just fine, and we have no issues, where TFTP will every time fail, and you'll be left with just a server that's hung until it decides to reboot. Okay, so with Wilson provisioning, we have the ability to instruct any server in our data center to run arbitrary code. All we have to do is put a flag into Wilson provisioning that says, I want this server to run this stage, and then reboot it. And when it reboots, it will run your code and then reboot again to local disk. But can we do this via an API? Of course we can. We're programmers. We can do anything. So Wilson API provides an API for running a sequence of stages that we call a plan and doing so asynchronously. As you request a plan, it will reboot the host via API, and as it checks into Wilson provisioning will talk to Wilson API and says, what stage should this host run it in? And as your plan is created, Wilson API will say it needs to run, say, the BIOS update stage. And that gets returned in the Pixie menu. The host sends into the Wilson RAM disk, runs the BIOS update, reboots, and the whole process repeats. In this way, we can run through a sequence of tasks with one HTTP call that returns quickly, and then you would just specify a callback, whether that be an HTTP callback or an email. Our system supports all of those. So, for example, let's say reinstalling usually consists of updating the BIOS, verifying the hardware, initializing disk controllers, installing an OS, running Puppet, and then doing final verification on the host. That's a lot if you had to do that manually. Wilson API collects these as a plan and triggers a reboot. The server contacts Wilson provisioning, and which goes to Wilson API, gets the BIOS update stage, that gets passed back through Pixie, the host boots into it, runs it, and then tells Wilson API that, hey, I have successfully done the BIOS update stage. Wilson API says, okay, great, and I will mark that as completed. The host will reboot, Wilson provisioning will again ask Wilson API what stage, and it will say, okay, next thing is we need to verify the hardware to make sure none of the RAM sticks have failed or all the SSDs are present. And this, again, the server will boot into that stage, run that script, and then again return Wilson API. Okay, I've successfully verified my hardware. I'm going to reboot now. And that will continue through installing the OS, running Puppet, doing verification, until finally we return to the user, okay, your plan is completed successfully. Your server is good to go. Now this is fantastic. I've often said I wish I had a system like this in my house for when I'm playing around with hardware. All I do is tell an HTTP endpoint that I want to install a host, and everything involved with that is done, and I just get an email when it's done. But with a fleet as the size that we run at Twitter, there's actually better we can do on top of that. It turns out that even trying to manually keep track of which hosts you want to install and when and all the steps required in that can be just a painful process. Turns out there are few key points in the life cycle of hardware, no matter what it's doing or what its purpose is. These are things such as when it first gets plugged in. We always want to burn it in, make sure all the hardware is good. We always want to install an operating system. There's the unallocated state where a host is just waiting to be allocated to a team. It's our spare pool for quick allocations. Then, of course, the hardware can be assigned to a team and running a specific version of an operating system or a specific disk configuration. Between a host moving through all these key events, there are always tasks we want to do, such as reinstalling an operating system, wiping disks, doing the burn-in process. These never change. So we wrote a tool to do that called Wilson Lifecycle. Wilson Lifecycle defines that when a host is moved from one of these states to another, a certain list of actions can be taken. Primarily, these have to do with telling Wilson API to go reinstall this host or wipe its disk or run through burn-in. But it also has the ability to talk to other services inside Twitter. We have separate services whose job is to keep track of various metadata about a host, such as who's allowed to access it or what team it's assigned to. Wilson Lifecycle is in charge of actually talking to those servers and saying, okay, I am now taking this host and assigning it to this team. And in that process, it will also tell Wilson API to reinstall it, configure it correctly, etc. So let's walk through a quick example. I'm an engineer. I want a host. I get assigned by capacity. This host is yours. They're going to assign it. They're going to tell Wilson Lifecycle, assign host XYZ to my team. Wilson Lifecycle will take that and say, okay, going from the unallocated pool to allocated to team XYZ. I know that for that transition, this server needs to be assigned in the metadata server, have its attributes set for things such as operating system and disk configuration. And then, okay, those are set. The next thing it needs to do is reinstall the host. So it will go to Wilson API and say, I want this host to go through the reinstall plan, which consists of the BIOS update and verifying the hardware and all those things I mentioned earlier. Wilson API will come back 30 minutes later, hopefully, and say, okay, this host is completely reinstalled, it's good to go. Okay, final thing is to mark the host as successfully allocated, and then it will return an email to the team saying, your host is ready to go. This is awesome for managing the synthesizer square. No longer do we have to think, okay, when we allocate a server, we need to make sure we assign its role or make sure it gets reinstalled. We just tell the service, hey, we're allocating this server to this team. And all the steps necessary for that to happen in our infrastructure is done. What comes out the other end is a ready to go host. All you do is upload your application and say go. This changes the way we think about servers. We don't think about servers as things you have to go poke and prod to manage. A server is just a thing which is in a state and you move it between states. Eventually, after hopefully several years of successful life, it winds up in a state such as it's being decommissioned. And we do that, make sure it's ready to be thrown in the dumpster, and then somebody gets to go and literally unhook the rack. So the process from plugging into the data center to getting rid of it is entirely made up of state transitions. And doesn't require somebody to sit there and think about, okay, well, what does the server need to do? As a bonus, there's one small problem with the way we manage servers at Twitter, and that is the majority of the operating system and applications surrounding that is installed via Puppet. Turns out when you're using Puppet to run thousands of manifests, that's a very time-consuming process. It wasn't uncommon to see Puppet runs of up to an hour for a server. That's not including initializing the disk, installing the operating system. That is an hour for Puppet alone. That's ridiculous. That's time consuming, especially when you have some of these storage boxes who don't want their server to be down for upgrades for very long. 2 hours of an install time is unacceptable. So we set out to look at how we can reduce that. It turns out the easiest way to do that is just don't run Puppet. Don't. Simple, right? Don't run Puppet. Don't run the OS installer. Those things are slow. They're time consuming. We're doing the same thing every time. There's the same base Puppet that takes forever. There's the same base OS that takes forever to install. Why do we keep repeating this on every host that we do? It's unnecessary. So what we came up with was to image a disk of a well-known machine. This is the exact same thing that popular things such as Docker do. That's why you can spin up a container in 30 seconds. They're doing the same thing. They have a copy of what an operating system should look like, ready to go, sitting in a file. And when you say, I want a new container, it just copies that and runs it. We do the same thing, except instead of doing it on your file system, we're doing it to physical disks. We take a snapshot of a fully installed host, save it to a place that has a very fast uplink because it turns out these images are huge. And when it comes to install time, when Wilson API says, or gets a request that says, I want to install a host, instead of that stage consisting of running an operating system installer and then running Puppet, it's just let me download the image and extract it onto the hard drive. That whole process goes from about, let's see, it was 5 minutes for the OS install, and like I said, up to an hour for Puppet. 2 minutes. 2 minutes for that entire process. We do run Puppet still after this to make sure that any changes in the past 24 hours are still accounted for, but that run itself only takes 5 minutes. And so now the entire process from first reboot to update the BIOS to delivering to the customer goes from 2 hours to 30 minutes. This has been fantastic for customers who, like I said, don't want a lot of downtime. It's fantastic for when we get a truckload of servers in. Now, instead of having to wait hours to know if the servers are good, we can install them and within 30 minutes and know that they're okay. Additionally, since this process is fully automatic, and great strain has gone to make sure that there are no visible changes from installing an OS and running Puppet to just copying it down via the disk imaging. This was rolled out to customers with no noticeable impact. Nobody even knew this happened. It just suddenly their installs were taking less than 30 minutes. As far as one of the bigger gains for managing hardware at scale, this is as important as any of the other automation talked about previously. And it turns out not a lot of people are doing this on hardware yet. So in closing, the automation we built at Twitter saves an unquantifiable amount of time. The fact that our dozens and dozens of teams who own hardware don't actually have to worry about whether or not their host is installing correctly or whether it needs an install at all once it got provisioned. The time saved is immeasurable. There's still sometimes that people have to worry about directly rebooting a host. However, that's still never done directly on the host. It's still Wilson API always handles that. And so we still have full tracking and control over how hosts are rebooted. With that, I do want to have a quick aside. So earlier I had Wilson API, IPMI sitting up here on these charts, and it's grayed out. The reason is it's not a necessary thing for the stack to function. However, we have IPMI control split out into a separate function because IPMI is terrible. One of my recommendations to anyone looking at doing this for your own fleet of hardware would be to avoid IPMI at all costs. If you can find ways such as talking to a host directly that's running and saying, hey, reboot yourself, it is far more reliable than using IPMI. We have had severe problems even once IPMI goes wrong. You don't know if it's a network failure, if the IPMI card just decided to die, or if the host is having power issues. One of our biggest failure modes is with like, well, we couldn't reboot the host because IPMI didn't respond. And we have no idea why. It usually requires a person to either look at it or sometimes even ask one of our guys in the actual data center to walk over to the host having problems and look at it or physically unplug it from the rack to reset the card. And by having an entirely separate service to worry about that, we can mitigate out and separate those failures away from the rest of the stack so that the rest of our system doesn't worry about IPMI and how frequent failures are. In closing, the automation we built at Twitter saves an unquantifiable amount of time. provisioning hardware at scale is fast and easy. We've done it. It is totally worth the effort it takes to build up systems like this. I know of at least one open source software that tries to do this. We haven't found it to be completely acceptable at our scale. Also, our system, I believe, predates it. But if you want to know more about this or how we did it, come talk to me after this talk. We have our booth right outside the door. And maybe this time we'll take questions. You know what number?
Repeat the question. Repeat the question.
Well, repeat the question.
So we were asked about if we could give an idea of what the scale of our fleet was. I will say that in the description for our QCon presentations, it refers to hundreds of thousands of servers.
So the question is, why didn't open source software need to be to our scale? Primarily, it was due to actually managing data about the number of servers. It wound up being slow and inadequate, and also parallel provisioning performance was very slow compared to the system we built in-house. Like doing 10 at once got very hairy, whereas we can do 1,000.
So you grayed out the IPMI box, but are you still using IPMI to control the server when it's not responding to changes?
The question is, do we still use IPMI even though it has all those problems? And the answer is yes. Because at the end of the day, it is one of the only ways to talk to a server that is powered off but plugged in. So we do use it, but we try to avoid it when we can.
Follow-on question. You mentioned that you're a Mesos shop. Does Wilson Lifecycle tell Mesos, hey, I'm going to take this server down, move all your tasks aside?
So the question is, do we tell Mesos when lifecycle is going to transition a host and either do something to it? Do we tell Mesos slave out from under it? And the answer is not yet, but that's actually one of the top features we're going to be working on soon. So yes, it will soon.
No.
It doesn't right now, but it will.
But one of the things that hopefully will come up in a later talk is that Mesos is amazingly resilient to that.
Yeah. It has really no problems with us just ripping a host out from under it. But if we do that with too many at once, those guys tend to come yell at us. Yeah.
So for the hardware, do you outsource also the build up, or you buy a component and you build it all in-house?
So the question is, how do we outsource the building? We work with ODMs and integrators. We select all of the components, and somebody does the assembly all the way to racking and shipping. The system's already cabled up in a rack for us.
So you talked about at 100,000 server scale, custom server builds makes sense. Do you guys have a sense of what order of magnitude is kind of the break even, where most of us don't work at companies with 100,000 servers? Where is the point where that makes sense? And I guess specifically, and maybe question number two is the validation part of the process. Any ideas, thoughts on hacks to bring down the cost of that?
So the question was, how do we handle the validation? Where do we think that we get this break even in terms of, is it worth it to do the engineering yourself? I haven't done an analysis that would say that maybe it's 20,000 servers, et cetera. I think we were saving lots of money when we were still in the tens of thousands of servers. when we've just done some casual looks at this, if I need to buy 2,000 servers, if I can save $1,000 on those servers, I have a $2 million budget to support developing those, and it really doesn't cost that much money in this kind of model, right? That's just a real simple computation that you can do. But it's I think where people are getting hooked, tripped up right now is it's really common when you're small to be in a cloud provider, and then you bring in this idea of having to move, like transition out, and it's hard to really put numbers around that.
And then the validation part,
The validation part, we work with, some ODMs are actually pretty capable of this, doing, let's say, a thermal analysis of the chassis, an airflow simulation. We've worked with partner companies to do shock testing, to do, you can outsource to somebody who's really good at shock testing or putting it in a thermal chamber to tell you how it's going to respond. It's surprisingly inexpensive when you're looking at saving, like I said, could it be several thousand dollars per machine? Please.
Are you going to open source Wilson?
We would like to, very much. Currently, though, we don't have the manpower to do that, unfortunately. My team is very understaffed, so that's one of our biggest requests when we talk about it in public is, are we going to open source it? Unfortunately, right now, it's no, but we want to.
And are you members of OCP? Do you think that's another way to save money is to go on the open compute platform?
That I think becomes a question of scale. I think that I can say that at a certain scale, you can get whatever you want, regardless of if somebody's going to make tweaks for it, they'll do that for you. But we haven't found that open compute was something that, it didn't really drive up the density in the rack for us. It was a different rack form factor, which that can actually have a significant impact in your data center. I think when you see who's really adopted it, it's only been the people that have contributed it. I think there have been some smaller adoptions, but it's been challenging for small organizations to do it because of EMI containment.
Quick question. The images you're referencing, is there a single golden image, or are you guys creating several images, and depending on what the image is, switches?
The question was, do we have a single golden image for our disk imaging stuff, or do we have separate images per role or use case? The answer is we have a single golden image. We found that it's far easier to distribute a single image and then do just simple, like I said, finishing up with an additional Puppet run to do specific tasks setups. Due to certain Twitter-specific environments, we are looking at doing some task-specific environments, but overall it's not necessary. We use a single golden image.
I think I will add to what Nick just said, that we do build one for each version of CentOS that would be deployed. All right, thanks everyone.
you.
I'm really glad you attended.